Welcome to our deep dive, everybody. Today we'll be exploring the world of fractal geometry.
It's going to be an exciting one. Fractals really are mind-bending.
Yeah, I hear the word fractal geometry and I'm kind of picturing those really colorful images, almost like psychedelic,
Well, yeah, I mean, those images definitely exist, and those are fractals, but there's a lot more to it than that.
Okay.
Really, at the core of it, fractals are about self-similarity. So it's this idea that a shape can be made up of smaller copies of itself repeated at different scales.
So like a tree, right?
Yeah.
Where the branches are kind of like mini versions of the whole tree.
Exactly. Or think about a fern, like each frond is like a little replica of the whole plant.
Right, so it's kind of like those Russian nesting dolls.
Yeah. That's a great analogy.
You open one up and there's a smaller one and a smaller one.
Exactly. But instead of dolls, we're dealing with shapes or natural phenomena.
Okay.
And the key is that with each level of magnification, you see essentially the same pattern, but at a smaller scale.
Wow. So how are these shapes actually created? Like, is there a formula?
Well, there are mathematical formulas involved, but it's sometimes easier to understand with a visual example.
Okay.
So for example, let's take the Sierpinski triangle.
Okay.
So you can imagine starting with a simple triangle and then dividing it into 4 smaller triangles. You remove the middle one, and then you repeat the process for each of the remaining triangles.
Uh-huh.
And if you do this infinitely, you end up with a Sierpinski triangle.
So it's like a recipe, but for shapes.
Precisely.
Okay.
Yeah, so instead of ingredients, we have shapes, and we repeat the steps over and over.
Gotcha.
Each step gets you closer to that self-similar pattern.
So this is already blowing my mind, but how do you even measure something like a fractal? Our normal ways of thinking about length and area don't really work when you have this repeating pattern.
Yeah, you're absolutely right. Our traditional measurements don't work very well with fractals.
Okay.
Like take the Koch curve, for example. It starts with a straight line, but then you repeatedly replace each segment with a series of smaller segments that form a bump. And what happens is the length of the Koch curve actually increases infinitely, even though it stays confined within a certain area.
Wait, so you're saying a line that's infinitely long can fit within a finite space?
Yeah, it's one of the mind-bending paradoxes of fractals.
Wow.
And it kind of highlights why we need a new way to measure these unusual shapes. And that's where the concept of fractal dimension comes in.
Fractal dimension. So is that like measuring the length, width, and height?
It's a little more abstract than that.
Okay.
Think of it as a way to measure how rough or space-filling a fractal is.
Okay.
So a smooth line has a dimension of 1, a flat square is 2, and a solid cube is 3.
Right.
But fractals can fall between those whole numbers.
So like 2.5.
Exactly.
That's wild.
Yeah. So for instance, the Sierpinski triangle has a dimension of about 1.58, and the Koch curve is about 1.26.
So the more intricate and space-filling the fractal, the higher its dimension.
Precisely.
Okay.
It's a way to capture that complexity in a single number.
Now, we've been talking about these really structured fractals, but I'm thinking about things like clouds and snowflakes and coastlines.
Yeah.
Are those fractals too?
That's a great question, and it leads us to the different types of fractals.
Okay.
We've got our purely geometric fractals, like the Sierpinski triangle, that are created through those precise rules, but then we have natural fractals, things like clouds, snowflakes, and tree branches.
So it's like organized chaos.
Exactly.
No.
Nature uses randomness to create these really complex forms, so we call these random fractals.
Okay.
And then there's a third category, quasi-self-similar fractals.
Quasi-self-similar fractal.
Yeah, like coastlines and mountain ranges.
Okay.
They have similar patterns at different scales, but they're not exact replicas.
So there's like a whole spectrum of fractals.
Right.
From the perfectly ordered to the more organic.
Exactly.
Gotcha.
And that's what makes fractal geometry so powerful. It provides this framework for understanding complexity across a bunch of different phenomena.
It's amazing to think that this concept that seems so abstract and mathematical is actually woven in to the fabric of the natural world. It's like nature has a code, and we're just starting to understand it.
And the more we understand about fractals, the more we can leverage their properties for different applications.
Okay, now you got to tell me about those applications.
All right, so let's start with something you probably use every day, your cell phone.
All right.
Fractal antennas can receive a wider range of frequencies because of their shape.
So my phone's signal is, thanks to these weird jagged shapes, I was just assumed it was magic.
Well, there's some engineering involved for sure, but fractals definitely play a role.
Wow.
And that's just one example.
Okay.
Fractals are also really useful in understanding complex natural phenomena, like analyzing river networks.
Right.
And you can actually link that to flood prediction.
So the structure of a river can tell us about its flooding potential.
Exactly. A higher fractal dimension, so a more complex network, actually means a lower probability of flooding.
So a more complex river means less flooding. That seems
I
counterintuitive.
know, right? But a complex fractal-like network means the water gets distributed more efficiently throughout.
So it's like nature's own flood control.
Yeah, built right into the design.
Wow, that's amazing.
And you can apply this to so many different things. The growth of crystals, the formation of galaxies. It's like a whole new language for understanding the complexity of the universe.
This is incredible.
Yeah.
It sounds like fractals are way more than just a mathematical curiosity. They're a fundamental part of how the world works.
And the applications are just expanding as we learn more.
Okay, so what are some other examples?
Well, there's this really interesting problem called the Kakeya needle problem.
Okay, the Kakeya needle problem.
Yeah, and it shows just how counterintuitive fractals can be.
Okay.
It's about finding the smallest area where you can rotate a line a full 360 degrees.
I'm trying to picture this. So I have a needle, and I want to spin it all the way around without bumping into anything.
Yeah.
And you're telling me there's a way to do that in a really tiny space.
The area can actually be arbitrarily small.
It just seems impossible.
It's one of those crazy things about fractals.
Wow.
One way to construct these spaces is by using something called Perron trees.
Perron trees.
Yeah.
Okay, you're going to have to explain those to me at some point.
Yeah, absolutely.
But what I'm getting from this is that fractals can create spaces that defy our normal understanding of geometry.
Yeah, exactly. And this leads us to another really interesting thing.
Okay.
Iterated function systems, or IFS.
IFS.
They're a mathematical framework for generating fractals, and they use something called contractive affine transformations.
Contractive affine transformations.
Yeah, essentially they're rules for shrinking, rotating, or reflecting a shape.
Okay.
So imagine taking a triangle and applying a set of these rules repeatedly. You can get something like the Sierpinski triangle.
So it's like a computer program for creating fractals.
Yeah, that's a good way to think about it.
Wow.
And you can use the same process to create images of natural phenomena like clouds and mountains.
So fractals aren't just about describing the world, they're about creating worlds as well.
Exactly. They're even used in image compression.
Image compression.
Instead of storing every pixel, you can use IFS to represent the image with a set of rules.
So you're compressing the complexity into a code.
Exactly.
This is blowing my mind.
Yeah.
It seems like fractals are everywhere. We've gone from antennas to rivers to image compression, and it's all connected by these self-similar patterns.
And we haven't even touched on fractal dynamics yet.
Fractal dynamics.
Yeah, that's where we look at how fractals respond to things like heat and sound.
Oh, wow.
That's where things get really interesting.
I bet. Okay, well, I think we're going to need a whole other deep dive to explore fractal dynamics.
Absolutely. There's so much more to explore.
I can't wait. Welcome back to our fractal adventure. Before we went down that last rabbit hole, we were talking about how fractals could be used to create crazy efficient antennas and even predict floods.
And that's just the beginning. You know how we were talking about how fractals can pack a lot of detail into a small space?
Yeah.
Well, that turns out to be really useful when you're designing all sorts of things like antennas and heat sinks and even artificial tissues.
Like artificial tissues, like for medical purposes.
You got it. Researchers are using fractal designs to create scaffolds for growing cells.
Oh, wow.
And it mimics the branching patterns found in natural tissues.
That's wild. So you're saying we could potentially use fractals to build replacement organs?
It's definitely a frontier in biomedical engineering.
Yeah.
But let's not get ahead of ourselves. We were about to dive into the world of fractal dynamics, remember?
Oh, yeah, fractal dynamics.
Yeah.
Where we left off, you were teasing us with this idea of fractals vibrating and responding to forces.
Yeah.
Now, I have to admit, that sounds a little abstract. Can you give me a real-world example of what that actually looks like?
Think about a coastline.
Okay.
It's a fractal writer.
Yeah.
But it's also constantly being shifted by the waves crashing against it.
Right.
That interaction, the way the fractal structure responds to those forces, that's what fractal dynamics is all about.
So it's not just about the shape itself, but how that shape changes and interacts with its environment.
Exactly. And this applies to all kinds of systems, from air flowing over an airplane wing to how sound waves travel through a forest. It can even help us understand how earthquakes spread through the Earth's crust.
Okay, I'm starting to see the bigger picture here. Fractal dynamics is about understanding how complex systems behave in the real world, not just as shapes in a textbook.
Precisely. And it's leading to some really interesting breakthroughs. For example, researchers are using fractal models to study the spread of wildfires.
Really?
By understanding how the fractal structure of a forest influences the path of a fire, we can come up with better strategies for prevention and containment.
So we're talking about saving lives and protecting ecosystems using fractals.
That's the power of this concept. It gives us a new way to understand these systems,
Wow.
which is important for everything from environmental management to public safety.
Okay, but let's go back to those vibrating fractals for a second.
Yeah.
How do you even measure the vibrations of something that's infinitely complex?
That's where we need to talk about the Fractal
The
dimension.
Fractal dimension.
Yeah, you see, in a regular solid object, vibrations travel as waves.
Right.
But in a fractal, those waves get trapped and localized because of the geometry. These localized vibrations are called fractons.
Fractans, so it's like the fractal version of a sound wave.
That's a good way to think about it. And the Fractal dimension basically tells us how those fractons spread and interact within the structure.
So it's kind of like measuring the roughness of a vibration traveling through a fractal.
Exactly. And this can tell us a lot about a material's properties. For example, materials with a higher Fractal dimension tend to be better at absorbing sound or heat.
So we could design materials with specific fractal properties to do things like control heat or sound.
That's one of the most exciting things in material science right now.
Yeah.
Imagine creating a building material that's naturally soundproof because of its fractal structure, or a new type of battery that can store more energy.
It sounds like we're learning to speak nature's design language, using fractals to create materials that mimic the natural world.
And here's another crazy application. Imagine a material that could change its color or transparency based on external stimuli.
Wait, so a material that could change on demand? That sounds like science fiction.
It might sound futuristic, but it's all based on the principles of fractal dynamics.
Wow.
By changing the fractal geometry of a material, we can control how it interacts with light, heat, and other forms of energy.
So we could have things like smart materials or adaptive camouflage.
Exactly. And even energy harvesting devices.
This is incredible. It seems like with fractals, the possibilities are endless.
As we understand fractal dynamics better, we're going to see even more innovations emerge. It's a field that's always pushing the boundaries.
Okay, but let's step back for a moment. We've been talking about how fractals can help us understand the physical world, but what about the world of math itself?
That's where things get really interesting. Fractals have changed so many areas of math, from geometry to topology to probability and chaos theory.
Yeah.
They've made mathematicians rethink some of the most basic ideas about space dimension and infinity.
Now, I have to admit, my math skills are a little rusty. Can you give me an example of how fractals have changed things in math?
One of the most famous examples is the Mandelbrot set.
The Mandelbrot set.
Yeah. It's a fractal that's created by a pretty simple equation, but it creates this incredibly complex and beautiful structure that we still don't fully understand.
So it's both simple and infinitely complex at the same time.
It is. It's a perfect example of how fractals can challenge our intuition and show us connections between different areas of math. The Mandelbrot set has connections to number theory, complex analysis, and even computer science.
Sounds like the Mandelbrot set is a whole other rabbit hole to explore.
It definitely is. But for now, let's stick with the broader implications of fractals for math.
Okay.
They've shown us new ways to think about problems that have been around for centuries,
White?
like the Kakeya conjecture.
Wait, is that the needle rotating problem we talked about earlier?
It's the same problem, but now we're thinking about it from a purely mathematical point of view.
Okay.
And the solution involves creating some super complex fractal shapes.
So fractals aren't just a visual thing. They're actually a tool for solving tough math problems.
Exactly. And they're helping us visualize high-dimensional spaces, which is important for things like string theory and quantum mechanics.
Wow. It seems like every time we learn something new about fractals, they reveal even more depth and potential. I can see why you're so fascinated by them.
And we've only scratched the surface. There's so much more to learn and discover about fractals and how they can help us understand the universe.
Well, I think our listeners might need a break to process all this information before we keep going.
Probably a good idea.
Let's give everyone a chance to catch their breath, and then we'll come back for the final part of our fractal journey. Welcome back to our Fractal Odyssey. It feels like we've journeyed from tiny atoms to massive galaxies, all connected by these self-similar patterns.
And we're not done yet. We've seen how fractals are revolutionizing fields like materials, science engineering, and even medicine, but they're also pushing our understanding of things like dimension and infinity.
Okay, so before the break, you were about to tell us about negative fractal dimensions.
Right.
And honestly, that sounds like science fiction to me.
I know, it's pretty wild. But it's a real concept, and it challenges how we think about dimensions.
Okay.
You know, we usually think of dimensions as whole numbers. A line is one-dimensional, a plane is two-dimensional, a cube is three-dimensional.
Right.
But fractals can have fractional dimensions like the Sierpinski triangle we talked about before.
Right. About 1.58.
Exactly.
But how can a dimension be negative? Does that even make sense?
Right.
Imagine a set of points that get more and more spread out as you zoom in.
Okay.
The gaps between those points increase so fast that the set actually takes up less space than a single point would.
So it's like the set is disappearing as you get closer.
It's a weird concept, I know.
Yeah.
But negative fractal dimensions might help us understand things like how galaxies are spread out in the universe.
So we could use negative dimensions to map the universe. That's amazing.
And there's even more to it.
What?
Just when you think you've got a handle on fractal dimensions, there's another layer. Complex fractal dimensions.
Complex, like imaginary numbers. Now we're getting really abstract.
It's a new area of research, but it's pretty exciting.
Okay.
Complex fractal dimensions let us describe structures that change over time.
So it's like a fractal that's always evolving.
Exactly. And this could be helpful for understanding things like turbulence, the way stock prices change, even brain activity.
Wow. So fractals can describe not just the structure of things, but also how those things change over time.
Exactly. It's like a universal language for complexity.
This is incredible. It makes you wonder if fractal geometry is so important in nature. Does that mean there's a hidden order to everything?
That's a great question. And it's something scientists and mathematicians are still trying to figure out.
I guess some mysteries are better left unsolved.
Maybe so.
But what I've learned from our deep dive is that fractals are so much more than just pretty pictures or math equations. They're a powerful tool for understanding the universe.
Absolutely.
And it seems like we're only just scratching the surface.
There's so much more to explore.
Well, on that note, I think it's time to wrap up our fractal adventure.
It's been a great journey.
It really has. To our listeners, keep exploring the world of fractals. Keep asking questions and keep being amazed by the complexity of the universe. Until next time.